Hi, my name is Cindy Peto. I'm a PhD candidate at Laboratorio Nacional de Soluciones Biomiméticas para Diagnóstico y Terapia at Universidad Nacional Autónoma de México. I'm going to present you my poster, Fabrication of Microelectrodes with Large Electrochemically Active Surface Area based on shrunk polymer film and rapid low-cost prototyping techniques. At LensBiodit, we try to develop devices or materials to solve medical problems. A current unresolved issue is biomarker monitoring at point of care to determine a pathological condition of a patient. Electrochemical sensors present themselves as ideal devices to monitor at point of care since they are easy to instrument, to functionalize, and to miniaturize, making them affordable and portable. In light of this, the aim of this work is to standardize an accessible, low-cost microelectrode fabrication method by taking advantage of a thermo-shrinkable polymer film to induce metal nanostructuring and by implementing benchtop techniques to define the shape of the electrodes. Of course, we want to evaluate the functionality of the devices as electrochemical sensors. We have developed two paths to fabricate such electrodes. Both start with a clean polystyrene pre-stressed sheet, and at the first one, we define the shape of the electrodes with a vinyl stencil, which is fabricated with a typical cutting plotter. Next, metal such as gold is deposited by sputtering, and the vinyl mask is lifted off. Finally, the device is introduced into an oven at 130 degrees to induce the polystyrene thermal shrinking. At the second method, no stencil is used, and the shape of the electrode is defined at the shrunk polystyrene slab by CNC micromilling. Since the shrinking of the polystyrene induces the wrinkling of the metal layer, these can be transferred into flexible substrates such as polydimethylsiloxane slabs. To do this, a self-assembled layer of MPTMS is deposited on top of the gold layer to promote good adhesion between the metal and the PDMS. Next, PDMS gel is casted on top of the device and cured at 60 degrees Celsius. Finally, the composite is submerged into an acetone bath to induce gelification of the polystyrene and be able to remove it from the surface. We made some physical and electrochemical characterization of the electrodes, and results are going to be discussed next. First, we managed to fabricate 3 electrode arrays on top of polystyrene substrates, and we managed to transfer them onto PDMS substrates with good reproducibility. At electron microscopy images, we analyzed that the wrinkle size was around 340 nanometers, and profilometry indicated that the average rugosity was 4.32 micrometers. We wanted to determine the electrochemically active surface area. To do this, we submerged the analyzed electrode into a diluted sulfuric acid solution, and we applied cyclic voltammetry sweeps. To determine the electrochemically active surface area, we integrated the peaks and normalized. We found a 14-fold higher electrochemically active surface area at the structured electrodes compared to flat electrodes with the same dimensions. Next, we wanted to understand what was the electrical behavior of the cell conformed by the structured electrodes. To do this, we performed impedance spectroscopy. Here we found that the impedance dropped as the AC frequency increased, which means that the electrochemical cell is behaving as a capacitor. Maybe this due to the high surface area of the electrodes. Finally, we wanted to validate the arrays as electrochemical cells. To do this, we first developed a standard method, which is cyclic voltammetry with the reversible pair ferricyanide. We managed to find the typical duct shape of such reversible system with high device-to-device reproducibility. Next, we made a calibration with ferricyanide in a wide range of concentrations, from 0.5 micromolar to 1 millimolar. We found good linearity, but concentration range dependent, and good limit of detection. Some devices have shown very high sensitivity towards the micromolar range. For example, 500 microamperes per micromolar at the 1 to 5 micromolar range. This is interesting because some biomarkers at physiological fluids are around this concentration. So, here we have presented a new method to fabricate functional microelectrodes despite using cheap benchtop techniques. Furthermore, we have proven them being useful as sensitive electrochemical sensors on a wide analytical range. And we think that this rapid, low-cost prototyping method will enable an application-specific biosensor to be created on demand. We want to thank Felix, Aaron, and Shipping Dink, and thank you for your attention.